Hi, my name is Bo Yun, and I'm here to present a time series forecasting with the data on daily website visit. The data has a number of website visitors to an academic teaching website that was collected from 2014 to 2020. To easily visualize and identify key changes, I decided to reduce it down to 500 days of data. There are 4 variables in this data, and page loads will be the response variable for the purpose of this study. For model fitting, both ARMA and ARIMA are used for univariate models, and multiple linear regression, vector autoregressive neural network are used for multivariate models. Here we see that the realization appears to have a seasonality, which can be confirmed by the slowly damping sinusoidal ACF. In the spectral density, we see a bit of wandering and some periodic behaviors. The most prominent frequency peaks are 0 and 0.147, which indicate a wandering behavior and a weekly trend. We'll keep this in mind as we explore different models. First, I wanted to check the stationarity of the data with the Dickey-Fuller test. The result rejected the null hypothesis, meaning that the data is stationary. However, this needs to be looked at further since it is very close to the 0.05 cutoff p-value and cannot be fully trusted by itself. Next, I wanted to visually check each condition of stationarity. Although it appears that it has a constant mean, it is the domain knowledge of being a daily visit data, along with the observed seasonality in the ACF, that break the first condition of stationarity. The condition 2 of constant variance is assumed in this data. Next, the data is split in half and each ACF is compared and verified to have a constant correlation. Overall, due to breaking condition 1, the data is concluded to be non-stationary. The final ARMA model is estimated with parameters that give the lowest AIC. Here, I validated the model with the last 20 days of data. It turns out that the forecasts were tracking the regional data pretty well. Also, a rolling window was used to calculate the average AIC across the entire data set. The ARMA model overall did a good job forecasting as it has the ability to converge toward the mean. Now let's take a look at the ARIMA model. First, using the overfitting table with AR6 and 8, the unit root term is identified. Next, comparing 1 minus b to the 7 and AR14 tables, the seasonality term is identified. Complex conjugate roots are associated with the seasonality and damping sinusoidal patterns on the ACF, and it is shown that the two of the conjugate roots are very close to the unit root, which is why the sinusoidal behavior is very dominant. After that, the final ARIMA model is estimated after differencing the trend and seasonality. Using the final model, the last 20 days are forecasted and compared with the actual data. Also, the rolling window ASC came out to be around 13 million, which is slightly less than the ARMA model. Short-term forecasts look okay. However, due to having a trend term in the model, the upward trend in forecasting continues to grow as well as the prediction limits due to the seasonal component. For long-term forecasting, this model is definitely not a good fit. Here in this new model with just seasonality of 7, I wanted to see how getting rid of the trend term helps with the long-term forecasting. The forecasts line up pretty well with the actual data in terms of counting seasonality. For this model, the forecast centers around the mean pretty well due to the ARMA component, while the prediction limits keep growing sideways due to the seasonal component. When feeding multiple linear regression model into the data, all 4 variables utilized in the model turned out to be very significant. ASC was 10,400, which is very good compared to other models discussed previously. Due to regressors being forecasted with the ARMA models, the resulting forecasts were centering around the mean. Here is the vector autoregressive model not performing as well because it assumes all the variables are stationary without any seasonality counted. Although seemingly a bad model, there's an interesting finding with this fan chart. We see that page loads, day, unique visits, and first-time visits provide more information predicting returning visits, judging by the small confidence interval. Next, I tried a neural network with known variables. And this picture is a multi-layered perceptron with 10 inputs of various legs, 5 hidden nodes, and 1 output, which is the forecast. The forecasts were pretty spot on with the low ASE. This time, the model that was created using the forecasted variables was much less accurate as expected. Here we see that the neural network was able to capture not only the seasonality, but also the overall trend as well. Next is an ensemble model that was created with an average of the past two models, multiple linear regression and neural network model. It performed fairly well as expected with ASE of 16,000. Lastly, all the models are compared against each other. The model with the best ASE over the last 20 days was multiple linear regression with ASE of only 10,000. However, it is important to note that it was based on the true values of the regressors. For that reason, multiple linear regression model will be limited to short-term prediction. For long-term forecasts, I would choose ARIMA 301 with a seasonality of 7 as it fairly stays within the reasonable range of typical internet traffic, and most importantly, does not have to take so much of uncertainties around the forecasted variables like a typical multivariate models. Not to mention, it is unrealistic to have the true future values of regressors. For further research, I wish to incorporate more explanatory variables, such as website maintenance schedule, school events, or conference that can possibly boost website traffic periodically. These extra variables can certainly contribute to a more powerful models. That concludes my presentation. Thank you for watching.